I welcome back all to the course on control system engineering. In this video, we are going to learn the different reduction techniques of block diagram to reduce and simplify the given control system block diagram. The reduction techniques of block diagram are also called block diagram algebra. So using algebraic expressions, relations, we can reduce the given block diagram or complex block diagram into a simplified block diagram representation. So now we'll see one by one what are the different reduction techniques available for reducing the complex block diagram into a simplified one. The first one, there may be a possibility of two blocks or two subsystems connected in a cascade form. So how to represent this in a simplified or single block? By already we have known that two block when they are connected in cascade, the overall or the combined gain or transfer function is given by simply the product of these two subsystem gains. So when G1, G2 are connected in cascade, the overall gain is equal to G1 into G2. So this is the first algebraic relation. And second one, when they are connected in parallel, if G1, G2 are connected in parallel, then these two are summed up. So the overall gain is given by G1 plus G2. So the input and output will remain same, and the signal node points will be same, but in the middle of input and output signal, whatever the system blocks are reduced to a single block. That is called reduction. And in third reduction point, suppose if we have a summing point at the input side and G is connected, a gain term is connected after the summing point. That means gain term after the summing point. Then how to make this before the summing point? Sometimes for reduction of the overall system or the overall block diagram, we need to shuffle sometimes the block and the summing point. That time what to do? So if you want to change the G block from after the summing point to the before summing point, what we can do is keep a G block before the summing point, and that gives an additional block G here. This represents, see, the ultimate point what we have to remember is before this simplification, after the simplification, the overall gain should not be different, both should be same. Such a way we can alter the blocks in any manner for our simplified purpose, simplification purpose. So here G before to after to before, it is changed. So summing point moved, define a block. So or block before the summing point, or you can, other words you can say summing point is changed to after the block, or summing point after the block. So after the block, if you want to change like this, so this is the block remain same, and summing point from here to here it is changed. Before moving this G block, the summing point after the G block, see the feedback is here 1. Feedback gain is equal to 1. When you want to shift this summing point to after the block, then we have to multiply this G with the feedback gain, that is equal to 1. That means, of course, anyhow one additional G block also you can place here. Anyhow, whatever the feedback gain is equal to 1, again that will be equal to 1 only. Simply, if you want to change the summing point from before the block to the after the block, then you simply multiply this G with a feedback gain here. Here 1, so 1 into G is equal to Z. The next one is, if you want to shift the summing point after the block to the before block, like this. After block is here, here before block it is moved to before the block. Then we have to multiply we have to multiply 1 by Z with the feedback gain here. Here this second input signal is equal to 1. Nothing is given means here say it is equal to 1. Gain is equal to 1. So that gain is multiplied with 1 by Z. So simply. So after to before. Okay. This is summing point moved from after the block to before the block. Similar way, takeoff point or pick off point, if you want to move from before the block to after the block, here before the block here, then it is shifted to after the block, before the block to after the block. Then what to do? You have to multiply the feedback or the second input signal with 1 by Z. Since G is the forward gain, have to multiply this with 1 by Z. Okay, it it should give the same equivalent model before transformation and after the transformation. Overall gain must be same. So if you want to shift the takeoff point before the block to after the block, have to take 1 by Z to the feedback signal. Next, moving a takeoff point after the block to the before the block. It's just a reverse. Just multiply with G. Okay, here. Suppose if you want to eliminate the feedback, if here the feedback system is given, then it's simply nothing but 1 plus or minus GH. Here it is plus or minus. Plus or minus. It is already known. If you want to remove this feedback, so we have to make it a single block by using already we have solved how to reduce this feedback. So we'll get G by 1 plus or minus GH. This plus or minus is depending on this sign. And when the unity feedback is given, H is equal to 1. Therefore, here it will become H by 1 plus or minus G only. When we want to swap these two summing points, you can easily exchange it. There will be no change. Simply this summing point to here and this summing point to here. You can simply reverse it. If these two are the summing points, you can easily simplify it. Now just see overall transformation still what we have seen in a uh, single step. See, we have combined the two blocks when they are connected in the series to a single block like this by multiplying these two gains. P1, P2 are given in the cascade form, so overall is P1, P2. When these two are connected in parallel, the simplified version is the sum of these two. And also we can represent like this way. If we want to make the feedback system, I mean second input signal to 1, you can also make like this. And if you want to eliminate the feedback, we can eliminate and make it a single block like this. And if you want to rearrange the summing points easily can be exchanged, because it is simply the summation at one point to the next point overall from the rightmost and leftmost end signals will remain same even in the middle if you exchange the summing points. So you can simply exchange it. Here and here both are exchange x and y exchange, both will be same. And if you want to rearrange summing points, um, of course it is also same x y z w x y w x y, and we can also combine or rearrange the summing points like this. Here two inputs are there, here also two inputs, and the third output of the first summing point is given as the second summing point. They're also same but representation is different. And here when moving a summing point from after the block to the before the block. So here uh, what we have discussed here, after to before, if you want to move one extra block, 1 by p will come in the feedback. And if you want to move the summing point before the block to after the block, then p will come in extra block. So after doing this, both sum will become, here it should be same only. Here x plus y into p is equal to z. Here also x into p, y into p. Both are summed up here and got same. So it should be same before and after. Here, here what it will come here? X plus y, that is into p. So here what you will get is x plus y into p into p in this block. After transforming it, after reduction, what it is showing, just here x into p, here y into p, here y into p. After summing this, what you will get here, xp plus yp. Therefore before and after transformation both are equal. This is equal to this one. So overall transfer function should not be changed. This you have to keep it in mind, so that anyway we can alter or rearrange in the summing points or takeoff points. And similar way, takeoff point after to before, if you want to change, have to keep it here second signal gain with p. If you want to transfer the takeoff point from before block to after the block, you have to multiply the second signal with 1 by p. Therefore similar way you can calculate this y value. Here this y value, this y value must be same, you will get same only. And here also takeoff point before this summing point, and here also you can take in a complex way. It's your wish based on the problem. And here takeoff point beyond the summing point, beyond the summing point, beyond the summing point to before the summing point, I mean from before the summing point to the after summing point. So after summing point we got like this. So this is the way we can rearrange the summing points by aftering, by shifting the takeoff point before the summing point to the after the summing point. Now let us see how to reduce the complicated block diagram into a simplified one. So why to reduce this block diagram? If we don't reduce, what will happen? If we have a complicated or a complex system block diagram, it's very difficult to analyze if we get any error in the middle of the system. It's very difficult each block to block. I mean, to analyze it, you have to derive the mathematical equations, and we have to correlate each block. And finally, if you want to correlate the output to the input, it you have to come across all the blocks. It's very difficult. So in order to simplify, to make others understand easily, it's easy, um, better to reduce the overall or complicated system into a small simplified version of the block diagram. That is the motive of reduction of the block diagram. In this block diagram, how to the reduction process is having some steps. So we randomly, we can't reduce the complicated block diagram, we can't get the simplified version. So if you have to follow some procedure, in that the first step is we have to combine the cascade blocks if there are any in the system. And second step is we have to combine all the parallel blocks. If there are any parallel blocks in the system, have to combine those parallel blocks first. And also we have to combine or minimize or eliminate the feedback loops wherever are there in the system. Wherever you can eliminate the loops, we have to first eliminate the loops. So in overall, the first three steps to eliminate the cascade blocks and parallel blocks and feedback loops. So we have to first start with this steps to go inside of the reduction process. And next step is we have to shift the summing points if you want to which is conveniently to reduce further the block diagram. So take look at the summing points where we can shift before the block and after the block to make further process simplify. And next, repeat these steps, not only the summing points, takeoff points also you can alter to simplify further block diagram. And same process you repeat it, first to fourth steps you keep on repeat it. And wherever the cascade blocks simplified, wherever the parallel blocks simplified, loops avoid it. Then shift the summing points and takeoff points repeatedly, and finally you will get the simplified version in a single block. This is the way of reducing the complicated block diagram. Now we'll see this reduction process with an example. For example, take this a complicated diagram which is having more three summing points, three forward gains G1, G2, G3, and two feedbacks. Two feedback gains H1 and H2. So how to reduce this? We'll see the solution now. So from the procedure, we came to know that first we have to look at where are the any cascade blocks are there, or any parallel blocks are there, or any feedback blocks. So we'll look at this point. See here, in this total system there are no two blocks connected in series. Here if you see G1, G2, G1, G2 in the middle we have summing point. G2, G3 also we have takeoff point. And G3, G1 also not there, very far in the middle, so many blocks are there. Two, one summing, one G2 is there. So we can't say all any of these two are in cascade. Similar way, there are no parallel. G1, G2, H3, G3, 3 are not in a parallel. And similar way, there is no simple feedback loop. There is no feedback loop at all. No direct feedback loop. So next, first three steps we can't do any simplification. Then fourth step we look at the summing points alternation or takeoff points alternation. Here if you look at the H2 block, if you this summing point, if you make before to the G1, then G1, G2 will become in cascade. So to make this cascade connection, we will shift this summing point from after G1 to before G1, like this. After shifting, what will happen? What to do? This feedback gain should be divided by Z1. 1 by Z1 we should multiply. So we have a change in this gain, and summing point is shifted to before the G1. Now you can see G1 G2 are in cascade, therefore G1 G2 are reduced to a single block G1 G2. Now G1 G2 and G3 are not in a cascade, those are not in parallel, and there is no direct, this is not a direct feedback, and this is also not a direct feedback. Therefore again what to do, we can exchange these two summing points to get this is a single loop. So we have exchanged these two. What happened? Any change happened? Nothing happened, because two summing points can be easily, adjacent summing points can be easily exchanged. So no reflect in any gain, that no alternation in the any gain of the system. Now here see this G1 G2 and H1, this is a loop. So feedback loop, we can reduce this or we can eliminate this feedback loop by combining this like this, G1 G2 by 1 minus G1 G2 H1. Here see H1 is having positive feedback, therefore we got minus in the denominator. Now this block and G3 block both are in cascade, so we can easily combine. After this we have, see, this block is having feedback path like this and it is negative feedback, therefore we have a single block like this. That block, how to reduce this loop we know already. This is say suppose overall G and this is say G H overall H, therefore how to reduce this overall feedback, G by 1 plus GH. So G is this much, H is this much. Now after simplification we will get this feedback loop is eliminated and the gain is like this. Now see, this is a single again loop, feedback loop, but here feedback gain is 1 unity feedback system. So again, like say this is overall G and H is equal to 1 by the formula 1 by G by 1 plus GH. We substitute and simplify, you will get like this. Now overall system, the complicated big block diagram is reduced to a single block like this. Now you can easily write the transfer function of the overall system. So this is block diagram reduction is useful for finding the overall system transfer function. Thereby we can study the behavior of the system. If we directly see the complicated block diagram, we can't understand, we can't study the system behavior. um, it's very difficult. So this is the reduction process. After reducing it, we have simply, we can write simply the system transfer function C by R is equal to this much. This is the overall transfer function. And if you see the second example, this is the second example. You find the transfer function of the block diagram, given block diagram, and see this is how many, we'll go step by step. First, any cascade blocks are there? I didn't find any cascade blocks here, and also any parallel blocks here. This is a loop. You can clearly understand feedback path, and this is like here it is given path, and so this is again a loop, and again here from this again we have a loop like this. So overall loop like this. So there is no cascade and parallel connection, we have loops only, so we'll concentrate on the loops. So we'll see the solution. First eliminate the loop 1, say this is the loop 1 and this is the loop 2. We'll eliminate the first, okay, say this is the loop 1, so eliminate this loop. Simply this is combined like this, already we know this formula. And now we'll come to the second loop. Okay, here the second loop is having the summing point. Okay, let us shift this takeoff point from here to this, before the block to after the block, before block to the after block, then this block and G1 block will become in cascade. Of course, it's not a problem. You can also do like this. We can also simplify this loop and we can combine in a cascade way after that. But it's good to see, um, to shift this takeoff point A point to B. Now it will become like this. So takeoff point is shifted from here point to this point, and this in the feedback this is multiplied with the same amount 1 by of this term. So 1 by of this term will become in reverse 1 plus g2 h2 by g8. After this, now you can see these two are in cascade. Simplify this cascade, and also this is the parallel connection. From here to signal is coming to this point, and same point to signal is coming this way. So this is the parallel connection and this is the cascade connection. So one by one we'll simplify. So this parallel connection will give this summation, and this cascade is like a multiplication, we already know. So here the cascade connection, here the parallel connection. And now we'll see this total is like a single feedback loop. Therefore, if you write like this is say total G and this is total H, therefore G by 1 plus GH, if you write and simplify, you will get like this. This is a way how to reduce the complicated block diagram into a simplified version. Before concluding this session, let me recall what we have learned in this video. In this video, we have learned different reduction techniques, like if the blocks are connected in cascade or parallel, and feedback loops, how to reduce it, and different ways like how to arrange the summing points before and after the blocks, and how to move the takeoff point before the block to after block, and after block to this before block, and various shifting on rearranging of different blocks to reduce the overall block diagram. And also we have learned the block diagram reduction with different examples. In the next video we will learn some more example of block diagram reduction with a different complex problems, and we'll see also if, if more than one input is given to the system, how to reduce the overall block diagram. Thank you.